The question that echoes through time: what if the beginning wasn't the start? What if the beginning wasn't really the beginning? Think about that for a moment. We humans, we're natural-born storytellers, aren't we? We crave beginnings, middles, and ends. But what if the universe's story is far grander, far stranger than our neat narratives allow? What if our chapter 1 is actually deep into a much larger saga? This question challenges everything we think we know about cosmic origins. When we gaze up at the night sky, at that vast expanse of stars and galaxies, we're looking back in time. The light from distant objects has traveled for billions of years to reach our eyes, so we're already time travelers of a sort. But can we push our gaze, our understanding, even further back? Back before the moment our universe, as we know it, burst into existence? It's a question that makes your brain stretch, in the best possible way. It forces us to confront the limits of our knowledge and the vastness of what we don't yet know. The question of before the Big Bang is perhaps one of the most audacious of them all. It sits right at the frontier of theoretical physics, where our most powerful theories meet their match. But that's where the excitement lies, doesn't it? On the edge of the unknown. So let's embark on this journey together. Fasten your seatbelts because we're about to dive deep into some of the biggest mysteries the universe has to offer. Now, when we talk about the Big Bang, what are we really saying? It's a catchy name, isn't it? It conjures up images of a colossal explosion, a cosmic firework display, but that's a bit of a misconception. The Big Bang wasn't an explosion space, like a bomb going off. Instead, it was an explosion space, everywhere, all at once. Imagine the entire universe, all the space, all the matter, all the energy packed into an infinitesimally small, incredibly hot, and unimaginably dense state. From that state, it began to expand. And it's been expanding ever since. The evidence for the Big Bang is compelling, woven into the very fabric of the cosmos. One of the biggest clues is the cosmic microwave background radiation, or CMB. It's like a faint afterglow of that initial hot, dense state, a baby picture of the universe when it was only about 380,000 years old. We see it in every direction we look. Then there's the fact that distant galaxies are all moving away from us, and the farther away they are, the faster they're receding. This is Hubble's law, a signature of an expanding universe. The Big Bang Theory describes the evolution of our universe. It tells a remarkable story of how, from that incredibly hot, dense beginning, the universe cooled and expanded. But the bang itself, that T=0 moment, that's where our current theories hit a snag. It's not the absolute beginning of everything necessarily, but the beginning of our universe as we currently observe and model it. Let's talk about that T=0 moment, the very, very beginning as described by our current models. Physicists call it the singularity. It's a word that sounds a bit ominous, and in a way, it is. A singularity in this context is a point where things go off the charts. Imagine trying to divide by 0 on your calculator. It just says error, right? The singularity is a bit like that for our equations. It's a point of infinite density, infinite temperature, and infinitesimally small volume. All the matter and energy of the observable universe crushed into a point with no dimensions. It's a concept that boggles the mind. The singularity isn't necessarily the true beginning, but rather the point where our current story, our current physics, can no longer provide a coherent description. So, if the singularity isn't the absolute beginning, what else could there be? One fascinating idea is that our universe is part of an endless cycle of birth, death, and rebirth. This is the realm of cyclic universe models, and one popular version is called the Big Bounce. Imagine our expanding universe, the one we live in now. What if, instead of expanding forever or ending in some other way, it eventually stops expanding? What if gravity takes over again on a cosmic scale and starts pulling everything back together? A cosmic contraction, the opposite of the Big Bang. Instead of a singularity, the universe could bounce. It would reach a minimum size, an incredibly high density and temperature, and then rebound, starting a new phase of expansion. A new Big Bang emerging from the ashes of a previous cosmic cycle. Section 5, Beyond Our Horizon, Eternal Inflation and the Multiverse. Another mind-stretching idea about what might have preceded our Big Bang, or at least our specific cosmic patch, comes from the theory of eternal inflation. You might have heard of cosmic inflation. It's a widely accepted theory that proposes a period of incredibly rapid, exponential expansion in the universe's very first moments, even before the hot Big Bang phase we discussed earlier. Inflation helps explain why the universe is so big, so uniform on large scales, and so flat. It's a powerful addition to the standard Big Bang model. Imagine inflation as a vast cosmic ocean, constantly expanding at an astonishing rate. Within this inflating metaverse, or bulk, little pockets can stop inflating locally. When a region stops its super rapid expansion, it can then undergo a more conventional Big Bang-like evolution, cooling down and forming a universe like ours. Our entire observable universe in this picture would be just one such bubble that budded off from this eternally inflating background. This naturally leads to the concept of the multiverse. If our universe is one bubble, there could be countless others. Section 6. Space-time's hidden fabric insights from loop quantum gravity. So far we've seen that the singularity is a big headache for general relativity, but what if we bring in the other pillar of modern physics, quantum mechanics? Quantum mechanics governs the world of the very small atoms, electrons, photons. General relativity describes the very large planets, galaxies, the universe itself. The problem is these two theories don't play nicely together, especially in extreme environments like a black hole, or the Big Bang singularity. That's where a theory of quantum gravity is needed, one that can unite these two frameworks. One leading candidate is loop quantum gravity, or LQG. Loop quantum gravity proposes something truly radical, that space-time itself isn't smooth and continuous as Einstein envisioned it. Instead, LQG suggests that space-time has a discrete, granular structure at the tiniest possible scales. The Planck scale, which is incredibly small. Imagine space-time as being woven from tiny, indivisible loops or quantum threads. This quantization of space-time has profound implications for the singularity problem. It essentially says that you can't squeeze space down to an infinitely small point. Section 7. A universe without an edge, the no-boundary proposal. What if the question, what came before the Big Bang, is the wrong question to ask? Not because time didn't exist, but because the universe, in a quantum sense, might not have a beginning or an edge in the way we intuitively think about it. This is the fascinating idea behind the no-boundary proposal, developed by Stephen Hawking and James Hartle. It's a concept rooted in quantum cosmology, applying the principles of quantum mechanics to the universe as a whole. The no-boundary proposal suggests that if we could travel back in time towards the Big Bang, as we approach what we call t=0, the nature of time itself would change. In this quantum regime, time might behave more like another dimension of space. So instead of a sharp starting point, a singularity where time begins, the universe would have a smooth, rounded-off beginning, much like the South Pole on Earth. In this view, the universe is finite in age and size, but it doesn't have a boundary or a starting point in time. It just... Section 8. The dawn of time itself, a quantum perspective. We've touched on how time might behave strangely near the Big Bang, perhaps even transforming into a spatial dimension in the no-boundary proposal. Quantum cosmology takes this even further, suggesting that time, as we experience it, this arrow that flows inexorably from past to future, might not be a fundamental property of the universe at all. Instead, time itself might be an emergent phenomenon. Think about wetness. Individual water molecules aren't wet. Wetness is a property that emerges when you have a whole lot of water molecules together. Section 9. The never-ending quest, embracing cosmic mystery. So, what existed before the Big Bang? As we've seen, there are many intriguing ideas, from cyclic universes and big bounces to eternal inflation creating countless bubble universes, and from the quantum granularity of space-time in loop quantum gravity to the no-boundary proposal and the emergence of time itself. Each of these theories pushes the limits of our imagination and our mathematical tools. None of them are definitively proven, of course. They represent the cutting edge of scientific inquiry, the bold attempts to answer one of humanity's oldest and deepest questions. The truth is, we don't know for sure what, if anything, came before our Big Bang. And that's okay. In fact, that's more than okay. It's exciting. Science is not about having all the answers. It's about the relentless pursuit of understanding, the joy of discovery, the willingness to embrace mystery and to keep asking why and what if. The question of pre-Big Bang cosmology forces us to confront the fundamental nature of reality, of space, time, and existence itself. It's a reminder that the universe is far more complex and wonderful than we can currently comprehend. These explorations are not just abstract intellectual exercises, they drive technological innovation, as we build new telescopes and detectors to probe the cosmos.